Good morning. All right, well, there are only 3 of us here right now, but we'll wait a few minutes, let other folks get signed on. Good morning, everybody. Pardon me here, I'm going to make an offline look-see. All right, we're going to get started here in just a moment. Give just a minute more for any latecomers to get in, and we'll get going. All right, let's go ahead and get started. First of all, I hope nobody panicked when the video of last week's class was off of the internet for a while. YouTube had flagged us as our videos being in violation of their usage policy, and had taken off the our video of Wednesday's lecture, at least temporarily. It looks like we got the appeal process taken care of, and it's back up though. The other thing, just to keep you informed, if you hear me over on this end groaning in pain, it is just that I spent my weekend at camp chasing Cub Scouts, and I might be a little bit sore. So on with our tossy things. So first thing, it looks like there are 5 of you who've started on the midterm. Good luck to everybody on the midterm. Let's talk a little bit about, I believe this is pretty close to where we left off last week at binary semaphores. And so let's talk about important things about binary semaphores. 0 with a binary semaphore is the condition that causes whoever is pending to stop. And so in general, if you're using a semaphore to control access to something, a 0 would mean that it's being used. If you're waiting for an event to occur, a not ready would mean that the event hasn't become available yet. It hasn't. It's not. You're not ready to execute based on the creation of the event. So important calls to remember are semaphore construct, that actually creates the semaphore pinned, that waits until the semaphore is non-zero. And what you need to remember about semaphore pinned is that it always decrements when it executes, as long as the value is not greater than 0. So semaphore pinned decrements the value back to 0 in the case of a binary semaphore. So as soon as you pinned on it, the next pinder is going to wait until somebody else posts. And of course, semaphore post is basically just an increment on the binary semaphore value. So, because I don't think I covered this in my lecture notes, but I'm going to remind you guys of it. I'm pretty sure I've talked about it. In an interrupt routine, which is not strictly speaking part of the kernel, when you're in an interrupt routine, calling semaphore post is just fine, because a semaphore post does increments and exits. It never. Doing a semaphore pinned in an interrupt routine is almost always a bad idea. If you have it as wait forever, then you have the situation where an interrupt could occur, and it's going to wait until the cows come home. But at the very least, if you have if instead of a wait forever, if you have a timed wait, it's still going to sit there for that period of time in that interrupt and not release the control back to the operating system. That can be a bad thing. Semaphore pins with a BIOS no wait flag absolutely can be done, and that in that case the pin doesn't actually pin. It simply tells you whether or not it would have pinned in its return code. And although that's perfectly okay to do, it is not advisable to do it. You need to figure out a different way to communicate with your interrupt functions. All right, so the semaphore params function is that one-time function that we create to get all of the pieces of the control block for the semaphore initialized. The semaphore struct is the actual data structure that has all the information about the semaphore that the operating system uses. Getting the semaphore handle, that is what we use. The semaphore handle is actually, if you look at the detail, it's best to do the call this way to get the semaphore handle. But in fact, the semaphore handle is nothing but a pointer to the semaphore structure, so that when you do a pinned or a post, it knows what the heck to do. It knows which semaphore to be dealing with. So I'm showing you the example of the most common way that we use semaphores. In this case, up in our main code, we're going to construct the semaphore, and we're going to get its handle in a function that would read the semaphore. The first thing that we do, and this is kind of a belt and suspenders move, but what we do is we do a semaphore pin. Since this is a binary semaphore, it absolutely assures that the semaphore is not in its one condition or the ready condition before we get ready to use it. Now, the reason for that is that if there had been a post without somebody pending on it before, then when we ran this A to D conversion call, even if the conversion hadn't been completed, that semaphore might already be set. So that just ensures that the semaphore is cleared beforehand. And notice the BIOS no wait. We don't care whether it was set or it wasn't set, but it absolutely will be 0 when we exit out of here. Then we call our A to D start conversion, and the intent of this chunk of code is simply to start an A to D conversion that is going to generate an interrupt when it's done. Let's go down here and look at what the interrupt does. The interrupt routine simply posts a semaphore that says, hey, we're done with the interrupt. Now we can pin on that semaphore, waiting for the A to D conversion to complete. We can read the A to D conversion and return it. And so this is actually a pretty good way on this sort of situation where you turn on a peripheral and you wait for it to give you an interrupt that the peripheral is completed doing whatever it's going to be doing. This is a pretty good way to construct that, and it's a very typical way to use a semaphore. So I'm looking over here. I don't know if any of you guys have got group chat up. Let's talk about priority inversion. Does anybody here want to tell me what priority, in your words, what priority inversion is? We'll give you a couple of seconds, see if somebody can pop up on group chat with that. It's okay to all talk at once if you wish on the group chat. And for those of you who don't know where it is, before I go on, I will tell you that if you take a look at the control bar for Zoom, there's a ... more. You can click on that, and there's a chat, and it also says that you can get there with the hotkey Alt-H. All right, so let's talk about priority inversion. So priority inversion is basically a situation where a low priority task obtains a semaphore, and that low priority task has taken its own sweet time about getting finished with its use of the semaphore, and a higher priority task now pins on the same semaphore. When that happens, all the mid-level tasks are going to have to wait until the higher priority task can take control. The higher priority task can do their thing. And so it causes the high priority task to take a longer time before it's ready to execute doing what it's doing. It's a bad thing. Now, you can't just willy-nilly say, okay, low priority task, you can't use that semaphore anymore. There's no telling what it is, at least at the operating system level, that you might be interrupting. So you have to figure out a way to get the lower priority task to get done with what it's doing as quickly as possible. So we do that by, instead of using a semaphore, using a mutex. A mutex works very much the same as a binary semaphore, but it has its own specialty. And in effect, what happens is that when you do a mutex enter, it acts like a binary semaphore. But if somebody else comes in and does a mutex enter on that same mutex, if the guy who is currently holding the mutex, if the guy who did the first enter is a lower priority than the new task pending, it will raise the task that has the mutex to the same priority as the guy who wants the mutex. And so and it's only a temporary basis. So until it gets ready to do the mutex leave, which is the same as a post, it's going to raise priority of that task. That means that the lower priority task now can execute more quickly and give control back more quickly to the higher priority task. Now, one of the things that's a little different about mutexes, we'll go down here and we'll look at the calls. So if you take a look at enter and leave, so enter and leave are from a semaphore standpoint very much like pinned and post, enter being the equivalent of pinned and leave being the equivalent of post. The big difference here is that you're not only passing the handle, but the enter returns an argument. And that is that this value that it returns, oh, and that's right, that is an int. There's an IARG. It's an IARG. That's what it is. There we go. Okay. So it's an IARG. And what it's returning here is, they call it the key. Basically, this is to make sure that whoever does the leave is the same one who did the enter. And so every time you call an enter, it creates a unique key handle associated with entering into this gate. And you just hold on to that. And when you get ready to do the leave, you pass it on to the gate mutex leave, and that's used primarily for error detection. But if you don't use it, your program will eventually crash and burn. So we do want to use it. Any other thoughts about semaphores before we move on? Questions? All right, so let's talk about a mailbox. So the purpose of a mailbox. Oh, can I explain what the handle is? Sure. Let's go back. I'll tell you what let's do. Let me see if I can pull up the TI documentation on on the mutexes, and we'll share that. No, that's not going to get me there. Not that one. I'm over here popping here. I'll show you what I'm doing. Let's see here. We'll do this. Okay. Let's see, what did they title it? TI Sys BIOS Users Guide. Can't type this morning. All right. So let's see what their explanation is for a gate mutex. If they're expecting you to take it on faith. Oh, wait a minute. I misunderstood your question. Okay, let's go back. The question is, can you explain what a handle is? I was going to explain the key. So here's what the handle is. The handle is, in effect, a pointer back to the structure that controls the mutex, controls the semaphore, controls the task, controls the timer. Every time we create one of these operating system entities that can do something that we have to reference, whether it's a mailbox, it's a whatever it is, we have to somehow be able to tell the calling function which structure that contains the information about the entity we're using is being used. So what we do here is that for the handle is in effect a pointer to the structure that we created when we did the construct thing. So I hope that's a good explanation. So the next question is priority inversion the same when using priority in a task? If so, does gate mutex fix the problem? So I'm not exactly sure that I understand the question. Is priority inversion the same when using priority in a task? So when you use priority in a task, what the idea is that that task at some point is going to depend on something, whether it's a mailbox, it's a semaphore, or it's calling a mutex. It'll pin. And the operating decides who gets to go next by looking at the priorities, and it takes the highest priority task and moves it on. So, so what happens though is, let's say that I have task A. Task A has, maybe I should type this. Let's do that. Let's do a new, we'll do a text document. Okay, so if I have task A, and he is priority 7. And I have task B, and he is priority 15. He's a really high priority task. All right, so task A takes semaphore Z or X, Z. So task A takes semaphore Z, okay? And the way he's going to do that is that he's going to do, so task A, he is going to do a pinned on semaphore X, okay? So that means that X is now 0. That's what that pin does. It takes the semaphore from whether it was 0 or not when he does the pin, it turns that semaphore to 0. And he's off doing his thing. So then task B, he also does a pin on semaphore X. But since semaphore is X right now is a 0, he's going to wait. Now the problem becomes I've got other tasks running here. So task A is going to be running until he gets ready to do his post. So task B can't run. He's just sitting there, even though he's a higher priority than task A. And if there are 3 or 4 other tasks, they can all run in this period of time, slowing task A down. Now what happens is that task A at that point then eventually will, task A will eventually post on semaphore X. Okay, and that means that X is going to become a 1 now. Oops, wrong way. And task B can resume execution. Okay, so that's the way it happens if we use semaphores. If we do it with the mutexes, then when we do so task A, this time task A is going to he's going to do an enter on mutex Z. Okay. Okay, so that's going to take Z, just like he was a semaphore, and set him to 0. Nothing interesting is happening beyond what would normally happen, excuse me, with the semaphores. But now task B does an enter on mutex Z. Well, mutex Z is still held by task A, and so what's going to happen is that he's going to wait and change priority of task A to 15. Okay? Now, task A finishes faster, okay? And task, and then he does a leave. So he does a leave on mutex Z, which is going to take Z, put a 1 in there, and it's going to change priority of task A back to 7. Okay, so that's what's going on here in inversion with relationship to task. Does that answer your question, Mr. Ramirez? Cool. I like it when I get folks when I can eventually explain things. I'm slow, but I get there. Okay, mailboxes. Okay, so another question here. If you're using the same task with different structs, is the priority also an issue? Yes. Yeah, so the task structure, you always have to use the same, obviously you have to use the same structure to hold the semaphores. But if you have one task that you have 2 instances of, they're using the same structure, it is no different than having 2 tasks that have different structures. And actually, they're not going to have the same structures. They're going to have, they actually share code space, but the structures for every task must be unique. Okay, let's talk about a mailbox. A mailbox is the way that you get a single value passed from point A to point B. Now it turns out with the TIR toss that you can make that what's in that mailbox an arbitrarily large sized value. So I could have a 50-byte structure, a 60-byte string is whatever I'm putting into my mailbox. The reason that we usually try to use pointer-sized things in the mailbox is those tend to be relatively fast to move around in memory. And if you're using a mailbox and you're having to copy big chunks of data back and forth, it'll actually slow the operating system down. So generally, we want to use something that's a pointer-sized or something relatively small is the value we pass in a mailbox. So in effect, what happens is that with a mailbox, it's a lot like waiting for your bills. You sit there and you look at the mailbox, and when something shows up in the mailbox, you can use it. And while you're waiting for something to appear in the mailbox, everybody else gets a chance to use the computer. So in effect, what you're doing is you're pending on an event, much like a semaphore, except this time what you're pending on is you're pending on somebody putting something in the mailbox, another task putting something in the mailbox. Now the TIR toss allows you to put multiple slots in a mailbox, which most operating systems call that a queue. But in effect, what happens is that it becomes a first in, first out, or FIFO buffer for mailbox items. So you can have somebody putting in 1, 2, 3, 4, 5, however big you've made this queue, items in that mailbox. And as long as there's something in the mailbox, someone pending for a mailbox read, somebody pending on reading that mailbox is going to get the value without pausing, as long as there's something in the mailbox. And we just talked about that. So let's look at the mailbox functions. Param inet, that's common to pretty much everything in the TIR toss. The mailbox, constructing the mailbox structure, again, pretty much common to everything in the TIR toss. Don't forget that EB, you can generally make that a null pointer. But you do want to check at least the return value for mailbox, which is a Boolean, because if you miscalculate size weird and wonderful things can happen that can be tough to debug. And some of the clues about that may show up in the code that's put in this error block pointer. So mailbox handle, much like other handles everywhere else, this just gets a pointer to the mailbox that we can pass around to people. A mailbox pin. So here's what happens. I pass the mailbox, the handle that I've just created, if I want to wait on a value in the mailbox. I pass it a pointer to a place where I'm going to store the result. So this is a pointer to whatever you have told this mailbox by this message size. This is a number of bytes. So whatever it is that you to that particular size, and what's going to happen is that when a value gets put in, it's going to copy it to wherever this pointer is pointing to. Timeout, you can put in a timeout in timer ticks, or you can put in a BIOS no wait, which means that you have to look at the return code to see if anything got put in the message, or you can also use BIOS wait forever, which says we're just going to sit here until somebody gives us a value. Post works exactly the opposite. Now, post is a little different here because in this case, unlike a semaphore, nothing can stop a semaphore post, because worst case, it either increments it or it doesn't increment it, but it's just goes in, goes out. Mailboxes are different, because if I go in to post to a mailbox and there's not room in the mailbox for something else, then we got to figure out how to deal with that. So if this timeout is set to a number of timer ticks, then it will, if the mailbox is full, it'll wait up to that number of timer ticks before it gives up. If you set it to wait forever, doing a post will simply sit there until until there's room in the mailbox, which means somebody else has to do a pinned, take something out of the mailbox so there's room to put something in. Finally, if you do a BIOS no wait here, you want to check to see if the post was successful or not. If you do a BIOS no wait, what that does is that posted if there's room in the mailbox and doesn't if there's not room in the mailbox, and that will always return. If you're going to post something from an interrupt routine, which is entirely reasonable to do, you can do that, but when you do that post, you need to do it with a BIOS no wait, and you need to have some plan for whether or not it's important to know that you tried to post a value, but there wasn't any room in the mailbox for that to happen. So one of the things that you can do for instance, that you might use this kind of a mailbox for in an interrupt routine is that same A to D conversion function that we did when we were in in our semaphore example. You certainly could have, instead of doing the posting of the semaphore, you could have actually read the A to D value and posted it in the mailbox. And then the routine that used it would simply pin on that mailbox, as opposed to pinning on the semaphore and doing the read. The advantage of doing it with the post is that you spend less time in interrupt functions, keeps your stack a little bit more shallow, not enough to, not really a bunch, but some, keeps the stack a little more shallow, and it makes it, but in terms of timing, very similar. You're just doing more of your timing in your interrupt function as opposed to doing your timing in your actual RTOS, where it's a little bit more controllable. So my preference would normally be to do it with the to do it by doing the read from, do the semaphore like I showed you initially, but this is certainly a way to handle it. And it might make the reading of the code in the task function a little bit more straightforward. So there's not much to initializing this except for making sure that we get the size correct. So as a for instance, this particular mailbox, I'm putting characters in, okay, so 1 byte. So if I'm having up to 20 characters stored in the mailbox, the size of the buffer for the mailbox is going to be the size of this basic mailbox element, which is something that TI defines, and it's none of our business what's in there. And this is the size of our data. And so the size of the buffer we have to allocate is this. I happen to know that there's a question about this on the midterm exam, and it's one that if you don't think about the answer is really easy to get incorrect. So you might want to go ahead and double check what we've done there. But the rest of this is pretty much straightforward. These are our declarations. We do the params init. We point to the buffer. We point that we've created, which is that size. We tell it how big the buffer is. We do a construct, and then we grab the handle, and we're off to the races on mailboxes. Is there any questions about mailboxes before we move on? Okay, let's talk about events. So events we talked about just recently, and we're using them in our latest homework assignment. An event is in effect, it's like an array of semaphores that all act together in some way. So an event instance can be composed of one or more events, each acting like a binary semaphore. And a task can post one event, or it can actually post multiple events at any time, depending on whether it posts it with an and or posts it with that's not true. It always posts it with an or. So depending on what the flag is, it may set more than one bit to a 1. Now, a task pending on the event can either pend on a selected group of events using a mask that are all set to having occurred. They're all set to 1. So in that case, the pend waits until every event that it's pending on is ready, or you can do it as an or, where it pends only until one of the events is ready. And I did not put in the example code in this. We might, I think it's more important to talk about this in the documentation stuff. I'm going to flip over to an old lecture on events, since I did not put that in here. Let's see, where did we do this? Timers, semaphores, mailbox, and a watchdog timer. Yeah, okay. So you can have up in the TI-RTOS, by the way, you can have up to 32 events in any event instance. And well, by golly, I didn't put down all the structure calls in here. I don't think. Did I? I did not. That's why I didn't include it. Okay, so let's run through that in the TI RTOS documentation. Let's pull that up over here. And let's go to events. Okay. So with events, yes, there we go. This is an important thing, and I think I did cover that. Only one task can depend on an event object at any given time. So it's important when you set up an event that you're not trying to set it up so that different tasks can depend on the same set of events without creating different event instances. That's really important. The event pinned. Now, the way that you pinned on an event is that you set an AND mask or an OR mask in general. You can set up both, but it really doesn't, as a rule, make sense to do that. What you're going to want to do is you're going to decide an AND mask, which means that all the bits that you set in here, the task for all those bits, have to be true for the pin to exit, or an OR mask, which is where anyone can be set true. And what you get as a result is that the output is always going to be what the event mask was when the pin exited, before the various events get cleared as a result of the pin being active. So you can use that value to determine which bits were set. So you know which bits were set if you exit from an AND mask and it's not a timeout, right? OR mask, it's more important to be able to know which bits actually got set, and that gets returned right here. And so their runtime example's not that interesting, and they don't have, okay, so and the event create is a straightforward call. Let's see if I can find. I will have for you guys. I'll send out later on today. I will send an example. I'm not sure that I've provided you guys with an example of an actual event initialization and use. I will send you guys out one today because I'm not happy that I don't have that there. I'm not happy with their documentation in this. So let's see. What is that? Implicitly posted events we're not talking about. We've already talked about gates. Okay. All right. So let's switch gears here to documentation. I'll ask you a few things about documenting your designs. So there are two kinds of documents that we can create. One are design documents, and what I mean by a design document is that's not so much trying to explain what it is that you've done, although that certainly is part of the purpose. But design documents are documents that let you break down what it is that you're designing into understandable components. So they're going to address things like, how am I going to structure this code? Where am I going to put the different functions? What functions am I going to create? they're going to do something about data flow. When I get information from function A, how does that information get to function B? That's what data flow is. Control flow, that's like a flow chart. Okay, so control flow is we're going to do step A, step B, step C in any particular task or sequence of tasks. You need to be completing design documents before you write the software. Now, I know that it's real easy to say, what do you mean before? Because I may change my mind, and that's absolutely true. But by writing the things that set out the structure, the data flow, and the control before you actually write software, what that gives you is that gives you the opportunity to think through the design rather than just hacking it. And yes, you're going to end up having to change this stuff. You do complete the documents after you've completed writing the software, but you need to get them as completed as you can before you write a single line of code. So implementation documents are things that you use to implement the details of what actually happened when you wrote the code. So number one, you're going to be doing things like addressing calling convention details. So you got a function that you designated as a function in your design documents, but now how do you actually call it? It can be used to improve the readability of code and can help you reuse things. And probably the best example of implementation documentation are the comments that you put in your code. Okay, the things that tell you what are the calling parameters and that sort of stuff. And one of the really cool tools that we can use that coding standards are set up to support, but I haven't required you guys to use it, but it's a good thing to look into, and that is Doxygen. So Doxygen goes through, it looks at the comments in your code, and if you structure them properly, it'll create a web page, a series of hundreds of web pages actually, that explain what your code does. It's really kind of cool stuff. And so you do this implementation documentation during and after writing your software. So design documents typically are going to be hierarchy charts, which I know you guys are familiar with, flow charts that I know that you're familiar with, control flow diagrams, which could be something like state machine diagrams, that sort of stuff. Data flow diagrams, which we've talked about in this course about which direction data flows. And sequence diagrams, which again, another variation on the theme of control flow and state machines. So implementation defined documents are going to be inline includes, file and function headers, creating man pages, or even creating example code if you're creating a library. So hierarchy chart, its function in life is to show how functions depend on other functions. The primary job here is to help you understand how to partition your code into different source files and subroutines. And as a tool, you can use a hierarchy chart to see if you have unintended dependencies or if you have duplicated code in areas. And they can sometimes show you how your source files are related as linkage units, that is, connecting them together with the linking system. Flowcharts. Okay, This is one of my pet peeves at Texas A&M because I don't think that we do a good job of explaining that, in fact, there are rules to flowcharts, that if you don't follow the rules, it makes it difficult to use them. So let's talk about some of those things. First of all, a flowchart can only define a single thread for a program or a function. If you're doing something that is an RTOS, if you're doing stuff in Linux where you have more than one function working together, you can't do that with a flowchart, because a flowchart can only express what's going on in a single thread. If you want to do more than one, you have to do multiple flowcharts. The standard flowchart symbols are well established. The important ones are the rectangle, which means that you're doing something. The rectangle with two vertical lines in it is used to indicate a subroutine. The diamond is a decision block. Only a diamond, only a decision block can have more than one arrow leaving it. Okay? Anything, if you have a function block, a rectangle, and you have more than one gazouta line, you've made a mistake. On the other hand, you have to label each exit out of a diamond so that people know why they're taking that particular path in the logic. If you need to make a decision that is not yes, no, or actually, you know, the diamond, if you only have one gazina, the diamond has 3 natural gazoutas. But if you have something where there are more than 3 ways out of a diamond, you can put a line on the bottom. You can have multiple lines coming out of the same place with them uniquely identified as being different types of exits, but only come out of with multiple out arrows out of a diamond. The other thing in a flowchart, every connecting line must have an arrowhead on it. Otherwise, it's really easy to get confused in even a moderately complex flowchart about, you know, which way the logic is flowing. So the last thing I'm going to talk about here are control flow diagrams. We've been using these pretty extensively, and basically what they do is they define how, in a multi-threaded program, you're going to move control and data around in the program. We have symbols that I've already given to you guys about what we're going to use in control flow diagrams, and you probably need to review that material as well. So, having said all that, you know, again, you have all my lectures. YouTube is now letting us post our videos again, so you can go back and review previous lectures. And you guys all have a midterm exam to complete. So are there any questions? We'll give it a couple minutes here in case somebody has some additional questions about the review. And I will get you an event example out today. All right. Well, ladies and gentlemen, go out and conquer the world. Have a great day, and I will get this posted as soon as I can. We'll talk to you later.